Right, so today we're going to be talking about. I wanted to teach friction, but then I was wondering what order to teach things in. I was going to teach masses and springs, but there's so much like prerequisite knowledge. I realised probably the best thing to teach would be normal reaction force, because we can't teach friction. Oh my god. We can't teach friction without the normal reaction force. Okay? And for this, you need to know your trigonometry. And for that, we got to work in radians. Now, technically, you don't have to work in radians because, unity has functions that work in degrees. But it's just best to think in radians. So the first half of this lesson is just going to be, I'm sure you've been taught trigonometry 300 times, but we're just going to drill down on trigonometry to make sure that you have been taught to things at a sufficient level to understand physics, because trigonometry is so important for everything we do. So, first of all, I'm just going to teach things a bit differently to how you've been taught it usually. Right, this, we're going to call this pi. Right? And we know in general what it really is. And can I just quickly shut the window because I got birds outside? Right. This, okay, if this is a radius 1, then this arc is the pi, right? But we're doing trigonometry with sine and cos, and we're going to be using unit circles for everything. As in, when I say unit circle, I mean a circle of radius 1 that starts at the origin, right? So we don't have to worry about. We can just look at this and call that pi. From now on, this is pi. Half a circle, that's pi. This is pi over 2. This, you stick two pi's together, you get 2 pi. You stick 3 of these together, you get pi over 2, pi over 2, pi over 2 is 3 pi over 2. Okay. So, this is a graph we're going to be drawing a million times. And I'm sure you're all seen this before and familiar with it many times in your life, right? This is the sine graph. Oh, that wasn't actually a bad sign. I'm pretty proud of that. So, okay, let's deep dive on this sine graph. You can see that this is a pi because it's a whole curve. It's literally just what we drew last time, right? It's half a circle. So this is a pi. This is half a pi. It's one of these semicircles. Sorry, no, like a quarter circle, right? This, if you imagine that this was a full circle, right, and it went this way, well, if we went round there, we'd be doing 3/4 of a circle, right? But instead we've gone that way. It's the same thing, though. So, this is that. It's 3 pi over 2. Here, 2 pi, because it's a full circle. This one, it's a circle and a bit. It's 5 pi over 2. 3 pi. 7 pi over 2. 4 pi. I want you to be able to look at this graph and just know these ones. I don't care about pi. I don't care about 30 degrees. I don't care about 45 degrees. I just want you to be able to look at a sine and know, okay, a sine graph, it looks like that, right? If you take away the curves, it goes up, bing bong, right? And at all these various points, it goes 0 up to 1 to -1. So the characteristic feature of sine is that it starts at 0 and goes up to 1, goes down again to 0, goes down to -1, it goes up to 0, up, down, down, up. So you just get this shape, and it's always going to go 0, 1, 0, -1, 0. And you don't care about it. Okay, obviously we do care about this curve, but in your mind, all you really need to know are these points of interest, and that's pi over 2, and that's pi, and that's 3 pi over 2, and that's 2 pi, right? And you need to know it like your times tables. You need to know, like, okay, here's theta, here's sine theta. Okay, well, what's 3 pi over 2? What's 6 pi? What's 7 pi over 2? What's 9 pi over 2, right? And what's 0? Well, sine 0, we know is 0. This, you know, it's 3/4 of a circle, so it's -1. Always is for sine. When you take a quarter off a circle, it becomes -1. Right, so this one as well, 7 is taking a quarter off a circle again, so that's going to be -1. This is a multiple of a pi. If it's a multiple of a pi, it's always going to be 0. Right, so 7 pi, 0. 9 pi, 0. 9 pi over 2, that's 1. Because it's 2 full circles, you know. That's 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's 1. Right? Hope you all get that, right? So, I mean, you've presumably done it many, many times, but I want you to just not think in degrees anymore and just think of these circles, right? If you've got a full circle or you've got a half circle, your signs are going to be zeros. And if you've got the start of a circle, you're at a 1. And if you've got the end of a circle, you've got a -1. Because your little sine waves are always -1, -1. Okay? So, let's look at cos. Now, cos, very much like sine, because it is a sine wave, it's just a little bit different, right? Should I draw the sine first or the cos? Let's draw the cos first. Okay. And now let's draw the sine. Okay. Near enough. It's not great, but, you know, it'll do. Okay. Now, if... do I want to draw again? Nah, we'll make do with this. Right. The thing about cos theta is, it's just the sine. It's the same as a sine, theta, but we add pi over 2. Right, and this is a phase. And a phase is just how much you move it away. Right, so this is... if I decide to just move this quarter of a pi, then that's my phase. As it happens, okay, let's just look at this, right? Here, these are supposed to line up. Imagine they're at the same position. It's really hard to draw a sine wave, okay? And it's really even harder to draw a sine wave and a cos wave on top of each other. But I can't be bothered plotting all the points out, so you just have to take my word that is there, and that's actually there. Oh dear. Right. So, I should have redrawn that. So either way, right? This, okay, if you look here, this is cos. Cos, and it's pi over 2, right? You can say we're at the first turn, that's pi over 2. Cos pi over 2 is 0, as we can see, right? Sine pi over 2 plus pi over 2, aka sine pi, right, is also 0, as we know. It's this, right? So you can see that all the difference is you shift this curve to the right by 90 degrees, and obviously my drawing got progressively worse there. I could probably just draw it a little bit better for you, right? You got that one, you can see it's always at every point 90 degrees behind, but otherwise they're identical functions. Okay, so what's the point in any of this? Well, let's go back to vectors, lesson 1, right? And we have vectors, and vectors have an x and a y, right? Okay, they're not real. In fact, let me dot this to show it's not real. They have an x component and a y component, and we can, we can say that this has a v dot y and it has a v dot x. And this x, if this is theta, is v cos theta. And this y is v sine theta. And you should just know this intuitively. You should be able to just know, right, we're going to be doing diagrams, and in the diagrams, there's going to be angles, and you don't want to be sitting there thinking, oh, is it cos or is it sine? You want to just know, yeah, this is cos, yeah, this is sine, right? And cos is always on the nearest side. And the reason you can tell this is, right, let's imagine that this is a really, low angle, right? Well, we know that cos 0 is 1. So we've got v cos theta, and theta is really small. It's just like, cos theta, right? This tiny little theta, v cos theta, it's just going to roughly be equal to v, right? Once it's fully horizontal as well, right? They're equal. Whereas this one, this is the, this is the other angle. We can call it alpha, right? V sine theta for a really small theta is actually just going to be about equal to theta. Okay, so you just want to know instantly that, okay, cos is on the same side. And the reason I know that cos is on the same side is because cos starts at 1. So when my angle is 0, we're getting the full vector out of it. Because this angle disappears here when further down the graph. Right? But say that again, the magnitude. Oh yeah. So yeah. Yeah, I just mean as a scale, right? So right. In fact, I'd segue right into what you just said. We know that v magnitude times v's direction is v, right? This vector v. Okay, and that is equal to v magnitude cos theta, v magnitude sine theta. Okay, for every vector, you got this little formula, and you can prove this is true because, say you've got your vector v. It's got an x component. It's got y. That's v. You know that v squared is x squared plus y squared. Okay, because of Pythagoras. I don't need to explain that. But see here, v squared equals, or we'll just do it in one step. V squared cos theta squared plus v squared sine squared theta. Right, well, that's the magnitude. Right? And you'll see that, so this magnitude is root v squared cos squared plus sine squared, right? And it just so happens that sine squared plus cos squared equals 1. So you've got root v squared equals v. Right, so there you go. That's. In fact, really, we've not proved this to ourselves. What we've proved is that cos squared plus sine squared equals 1. But, okay, what does that actually look like? Because, okay, it's one thing knowing that cos squared plus sine squared is 1. It's another thing to think, what is sine squared? What does it look like? Why does this matter to me as a game developer? Because when you're in school, trigonometry, it just seems pointless, right? I just find out where the triangle is. But in game development, I might want something to bounce along the floor, right? And I might want to use trigonometric functions for that. If I'm just animating something quickly, like a UI element, I just want something to move around the screen a little, then I can use trig so I don't have to simulate exact physics, because it just works, right? It just works like a system, like a bouncing ball. Well, I'll get to the bouncing ball in a sec, right? So that was the worst line of all time, considering I have a straight line tool. Right. We have sine wave. Not bad. Okay. Not great, not bad. This, let's square it, okay? So, square of 0, 0. Square of 1, 1. Square of 0, 0. Square of minus 1, 1. 0, 0. 1, 1. 0, 0. Minus 1, 1. 0. So you see that sine squared is going to look like this. It's actually shallower and steeper. It doesn't bounce, right? It doesn't bounce like that, right? It curves like this. Okay? Okay, it was going so well. Right? Meanwhile, let's put in cos. So cos, trying my best. Not terrible. Okay. Now let's square this one. 1, 0. Again, minus 1 squared. 1, 0. So you see, they always stay above the line is the point. Right? Now these are all supposed to line up with each other. So this cos squared graph looks like this. And you can see that cos squared is the exact inverse of sine squared. Just don't look at the green line or the black line, just look at the blue and the red, and look, it's like DNA, right? It's like, well, actually it's not like DNA because the helix is a bit different structure, but whatever. It's like your sine squared is like this, and your cos squared is like this, right? And at any point, no, I'm stupid. It's totally not like that. Why have I done that? Okay, sorry. It's like your sine squared is like this, and that should be more curved. And your cos squared is like this. Okay? And so we'll draw a line over that. Okay, it's actually increasing energy. So this is really like a video game engine. We'll get back to that at a different time, but this is indeed what happens in a video game engine if you're not damped. The energy will increase. It's not supposed to, but it will. floating point errors. We'll get to that, right? But if you see here, 1 plus 0 is 1. 1 plus 0 is 1. 0.5, you see at this point, the blue is 0.5, the red is 0.5, 0.5 plus 0.5 is 1. If you take this point here and add it to this point here, then they'll add to make 1. The whole time, if you add these two up, they're gonna, if it was drawn correctly, they're gonna add up to make 1 in this bar. Okay? Now, there's one other identity that I'd like to teach you that you may have read this identity before in maths, but it's nice to know it and not just read it and see it in a graph and see why it is. Because the thing is, it's useful to be able to know the difference between different trigonometric functions so that you can tweak yours. Because I want to give you the knowledge that's in my head, and part of that knowledge is trigonometry is really cool and useful in video game development. And if you can just go, oh, this is motion slightly off, but I know why, it's because the frequency's wrong, or I know why, it's because it should be a cos instead of a sine. If you understand what these graphs are supposed to look like, then you'll understand how to make things move nicely. So I want you to, you don't have to take this in, right? But if you take this in, it will be useful potentially for you, right? So you've got your, let's imagine again you got a sine wave, right? And you got your sine squared wave, which is like, oh my god. That. Right? That last one was terrible. Now, if you want, okay, let's say we want to get this sine squared and make it more like a normal sine wave, or like a cos wave, because sine and cos are practically the same thing, right? Let's say we want to make this a normal wave. Instead of, right now this is stuck above the surface. We're just going to try and transform this until it's normal again. Right, so the first thing we can do is subtract 1 from it. Right, so if the red one is sine squared and the black one is sine, then this green one is going to be sine squared minus 1. Okay, and it's going to look like this. You know, it's just going to touch the top of there. All we've done is move it down. Okay. Well, we're not quite there yet. We need to make them go higher now. So if you imagine here, this is 2 sine squared, right? 2 sine squared is going to go even higher. Okay. So let's do 2 sine squared minus 1. It's going to go up here. Okay, and you see now, we just have like a normal, the wave kind of breaks down over there, but this is looking like a normal wave now. It looks like a minus cos wave, right? But the difference is, okay, do you know before I was talking about how sines, they look like this essentially? Well, a cos always essentially looks like that. Just, You can add the curve to it, but it's just a V. And the sine is just like a sawtooth. So if we have, if we examine this cos, the whole thing is only happening, okay. Look at the black line a sec, right? The black line's a sine wave. One sine wave is all this way across, right? But the cos, this new cos wave we have, is only halfway. right, is finishing here. So if we put, instead of using cos theta, if we use cos 2 theta, we'll stretch it out to be like a normal wave, right? So at that point, this thing, 2 sine squared minus 1, is equal to a minus cos 2 theta wave. Okay? And that means if you invert it, cos 2 theta equals 1 minus 2 sine squared theta. Now that's a trigonometric identity that you'll learn in maths. And I don't know, I was never taught to look at it like this, where we started with this red wave, we subtracted 1 to move it down to this green wave, right? So we got the minus 1. We doubled its height to get the term. Then we stretched it out 2 times, and then we get this trigonometric identity. And this is just true. Cos 2 theta equals 1 minus sine squared theta. And what's the point of that? Well, if you're moving 2 things at once, or I want my scale to move. I want to rotate a bit while I scale, right? But I want the scale to stay positive. I don't want it to go small. I want it to start from 1 and go a bit on top, right? Because that's the joy. That's the joy of sine squared, is that it's always above the line. So if you have a scale in your game, and you want to make your little creature scale up to there and then back to 1, and you don't want it to go negative, then if you use sine squared, it's going to go whoop, 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 right? But maybe you want him to rotate at the same time, and so you're going to take his z rotation, and you're going to move that. Well, then you got to know that if you want them to move at the same time, then you're going to want to use, sine 2 theta, right? Well, no, you never want to use that. You'd want to use cos 2 theta, right? But then you're like, well, that's going to start me on the right side. So if you know these little identities, it makes it much easier for you to do these little tricks. And we will get into these later when we study the wave equation. But meanwhile, we need to get onto the thing that's going to teach you friction. Right. So that was a nice detour, but let's get to the meat of why I wanted to get you at trigonometry. We'll come back to trigonometry. It's going to come up a lot. But first and foremost, you need to know, if this is a mass and it's sitting on a slope, it has a force down of mg, right? If this is theta, this angle is also theta. And if you don't believe me, let's make it really thin. Right? Oh my god, that was stupid. I think you trust me that that's the thin angle, right? It's definitely not the fat angle. Okay? So this, we know that if it's on the near side, this is going to become mg cos theta. And this is going to become mg sine theta. If we split it into these 2 components. We've got this component, right? And we want it in terms of the slope. So we don't always want stuff in x and y. We want them at weird angles. So, we want this angle relative. We want this direction and this direction, because that's the motion we care about. The reason we care about this motion is this, remember Newton's third law, experiences a reaction force. So this thing is pushing down on the slope. It has a weight here. This is its weight, mg, right? And then this is the force, the component of the force that it exerts directly onto the slope. so it receives an exact same force backwards. So the only force that it actually has down the slope is this. And let's say it's made of ice, so there's no friction. I know there is friction on ice, but pretend there's not, right? This isn't going to move into the slope. It's only going to move down, and it's going to move at this speed. Okay, so if we imagine there's a person here, right? Then now, let's rotate the whole world. Roop. Right, we've got our mass. Okay, here's the person. We only turn the camera, right? If you turn your head, you know, gravity's still this way. Okay? But the difference is, if this is mg, this is the mg cos theta, right? You know, now we've got it in terms of its y. Okay? Where this is theta. Okay? This, that's wrong. No, it's not. This is also mg cos theta. So this is in equilibrium. Static equilibrium. In this axis, right? I hope you understand that we've rotated the world here. So you can see that this thing is just going to move down here by mg sine theta. Okay. You can actually figure out how much it's going to move as well. Because if you think about how the engine then splits up the movement, right? It has a force that it's resolving in this direction of mg sine theta. So ma equals mg sine theta. A is g sine theta. In this direction. Well then, if you look, if your acceleration here is g sine theta, and then this is theta again, then if you then find out how much you're going to move down every frame, it's actually going to be g sine squared theta times dt, right? Because if you've already got this sine theta, now you're splitting this into an x and y component, right? So the amount you move left is going to be g sine theta cos theta, because it's your g sine theta times this component of it, cos theta. This component is sine theta, right? So you move left that times dt, you move down that times dt. Luckily, you're never going to have to program that because your collision detection will do that for you. You know, Unity just does this out of the box. But if you were curious about like how, if you ever needed to know like, oh, where am I going to be? How much is my my y velocity going to be in a frame if I'm on a slope, right? It's going to be this times by, this is alpha, you know, that's theta. Sine theta again, because it's on the opposite side, so you're using sine, not cos. This one's the same side, so you use cos. Okay, so again, what's the point? What's the point? Well, one thing that this is useful for, and this will be your assignment, is, let's say you have a little person. I don't know why he's angry, but he is. And he's fallen down from the sky, and he's landed on the floor. Well, there's a lovely, in Unity, function called onCollisionEnter 2D. And it takes a collision 2D hit. I call it hit. Right? What you can say is, first you can say, if hit's null, as in if it hasn't hit anything, right, return. it shouldn't be null, because otherwise it wouldn't hit something, right? But you've got to be careful, right? So then what you can do is hit this collision 2D has a thing called contacts inside it, and the contacts are these points. So let's say, you know, you land on the floor and there's 2 points. This is like contact 0 and contact 1. This is it's an array. So you can grab the 0th element, because especially in 2D games, you don't really care when we're doing what I'm about to tell you. Right, what we're going to do is we're going to figure out when our character can jump. And when our character can jump is when we've hit a slope. Okay, we've hit the ground. So we can grab the hits.contacts, and it has something on it called normal. And the normal will give you, for this contact, right, it will give you basically the normal reaction force, except just from 0 to 1. Okay, so it's not going to give you a force, it's just going to give you the direction. It's normalized, right? So you get this normal, and this has a y in it. Okay, so your character lands, you've got on collision exit, on collision enter, you can grab, and it takes, you know, collision hit. You can grab hit dot contacts, grab the first contact because you don't care about the others, dot normal dot y, right? And if you imagine it's you're on a flat ground, this normal is going to be the y. Remember, y is the sine of the angle, and there's no v this time because it's normalized, right? So this is just going to be that, and x is just cos theta, right? But we only really care about y when we're talking about whether you can hit the floor, right? If you hit the floor here and the angle's 0, then, you know, you're going to hit the ground at sine 0 is 1. So you're going to have a y normal of 1. If you've got 90 degrees, right, then you've got sine pi over 2. That's 0, right? So you see here, if you're not going to get, if it's at 90 degrees, then you're not going to, essentially if you're at a wall, you know, you collide with the side of a wall, right? Then you're not going to get any y normal. And I hope the point of this is, if you land on a mountain in a video game, you don't want your character to be able to jump, because if your character can jump up the mountain, then they can just glitch your game out, right? If you imagine you've got a really tall mountain like this, and you give them their jump back every time they hit it, they're just going to exploit it and jump, and go up the mountain. You only want them to be able to jump up your mountain when it's at a reasonable angle, right? So here, you know, I can climb this. It's allowed, okay? So the reason being is the normal dot y is less than a certain value, right? And those values will be, say you've got 45 degrees, that's pi over 4. Well, that's root 2 over 2 sine pi over 4. This is this number I told you in lecture 1 we'd see everywhere, 0.707, right? You can see essentially, right? A brick wall, if you collide with a brick wall, you will have a normal of 1. If you collide with a perfectly 45-degree slope, you'll have a y normal of 0.707. if you're at 30 degrees, which is pi over 6, right? Sine pi over 6 is a half. So if you decide, okay, well, I want it so that if my character is on a 30-degree slope, then they're going to be able to get their jump back, right? Then you can start a function called on collision enter hit. You know, you take that thing, you can say if the hit contacts the contact points, just in case that's not clear, the contact points which touch the slope, right, of 0, because you don't care about 1, 2, 3, you just only care about the first one, dot normal dot y is less than, for instance, 0.5, then grounded is true, right? So what that means is, if you hit the ground and this angle is less than 30 degrees, then your character is going to get their jump back. And, you know, if grounded is true, you're allowed to jump. We'll get to jumping later. We will, in fact, implement a jump. But that's essentially what I want you to do for your little homework, is just come up with a system where your character can land on the ground. You use your normal to work out whether they're on ground, on a too steep a slope, or just a slope that they can jump off. Okay? Right, so now let's go in the engine. In fact, we can do one more little thing I want to show you. Right, we were talking about sine squared before, right? And it looks like this. Well, another magic function you might want to know is, so that's sine x times sine x, right? You can do math.abs sine x, and that will look like this. Boing, boing, boing. Because if you imagine a normal sine wave would go down here, right? And you're just absoluting it so it goes back on the top. And you see that it's less smooth than a sine squared wave. And I can demonstrate it for you here. Right. Let's get rid of this one. Do you see this one? Do you see how it's bouncing? This because this is using abs, right? And now we'll get the other one. This is using sine squared. So you see sine squared is good for things like a fairy that's floating around or dust in the wind, whereas abs is good for something that's just bouncy. And then you can also see that if I just make another one of these, make it cos, and then don't square it, but double the frequency. I hope this works. I've not actually tested this, but we'll see. This should be the same. Oh, I need to make it minus. I put it in the wrong place. I've done something wrong. But you see the point that that sine squared and the cos. Oh, I've not added 1 to it. Of course I haven't. Because I can't do that just from this function. All this script is it's taking a y position, it runs it through the wave equation, which we will get to later. And then if it's squared, it squares it. If it's bouncy, it abses it. And then it just moves it and once it gets to the right of the screen, it teleports it back to the left. That's what that does. And then sets it. Right. So that's how the graphs, you know, appear in real life. If I show you another one, okay. Let's get rid of this one a sec. We're gonna make this one. Okay, let's edit them both. Frequency of 1, amplitude of 1, one's sine, one's cos. You see that they're 90 degrees off from each other, look. Right? So they're not opposite to each other, they're 90 degrees off. Now let's make this one cos and this one's sine squared. Sorry, no, this one's sine squared. Right. Let's make it a different color so you can see better. So you see this one smoothly walking on the top, right? It stays on the top half only, it never goes down. Whereas this one goes all the way down and up again. If you just look at that one, that's just a sine wave. If you look at this one, that's a sine squared wave. So it's really easy as well to get it running in your engine. It's literally just a line of code. And you can get all kinds of nice fluid motion, and we'll get into actual uses of this later. Is there any other equations that I kind of showed off? I could show you cos squared versus sine squared and show how they'll always add up to 1. Let's see. Cos squared, sine squared. You see that? So this is the 0 line at the bottom, right? And the top line is the 1. If you add their two positions, they're always going to add up to this top line. Okay. Anyway, if it was overwhelming, we did cover a lot of trig here. But I don't know, I mean, you'd have learned trig before. But I know we did a lot of mathsy stuff today. This stuff, if you don't get this right now, it's okay, because we're going to be doing a lot more of it when we get to friction, which is in 2 days. So we'll cover more of this. But for now, focus on this, getting your y normal, as in the direction you hit the slope on. Right, so there it's that direction. If you hit a wall, it's that direction. It's always basically opposite, away from any slope you've got, right? So I don't know if anyone feels I need to either go over more of this, or please, Alex, never do trigonometry again. Okay, cool. I'll see you all on another time.